and welcome back to another exciting episode of Miss O'Day's geometry class. So these are the 10.2 notes. So before this, you should watch 10.1, parts 1 and 2. So 10.2 is all about arc measures, and arcs are pieces of a circle. So we're going to be talking about those in degrees. So something we want to make sure we remember is that circles have 360 degrees in total. So because that's kind of what everything we're going to work on is based on. So the first thing we're going to talk about is a central angle. So a central angle is an angle of a circle whose vertex is the center. So remember, when we talk about angles, they always have a vertex. So here we're talking about inside a circle, the vertex is going to be the center of the circle and it's going to go out to the edges. So here we kind of are working with two separate things. We have arc AB, and the way we show it's an arc and not a line segment is we kind of draw this little arch over it. So arc AB, we would call that a minor arc. If I wanted to go from A to B the other way, the way I would know I was talking about the longer way is I add in a letter. So I would go A, D, B. All right? And that is called a major arc. So those are the two differences, and the way we talk about those is in length and measure of the angle. So a minor arc, when we talk about a circle, if I was to draw a diameter, that would be 180 degrees. So exactly half would be 180. So a minor arc is going to be less than 180 degrees, and a major arc is going to be greater than 180. The difference is, are you going the long way or the short way? And if you're doing exactly half, we call that a semicircle. So that a semicircle is exactly equal to 180 degrees. So here, I want to know, there should be little m's here. I want to know what the measure of arc RS, RTS, and RST is. So the measure of RS right here is based on that central angle measure. So it's 110. RTS is going, starting at R, going to T first and then to S. So that's essentially the 360 without this 110. So that's how we're going to find that. So that's 250 degrees. And then RST, you'd go this way. That's making that straight line with the diameter, so that is 180 degrees. Okay? So the arc addition postulate is pretty straightforward. It's very much like the segment addition postulate. So essentially, the measure of an arc formed by two adjacent arcs. So adjacent means they're next to each other. So if an arc is formed by two adjacent arcs, it's the sum. So how do we find the sum? That's with addition, okay? So here, if I wanted to find the measure of arc ABC, I know it's the long way because I have to go from A to B to C. I'm going to find that by taking the measure of AB and adding it to the measure of BC. So those are those measures I'm working with. That should be pretty straightforward. So when they're next to each other, we can add them together. Something you might be familiar with is this, the idea of a pie chart. It can split different pieces up by percentage. So everything is 100% in total. Half would be 50, a quarter would be 25. So that's kind of how this is based on. So this is in percent, I want it in degrees. So 100% would be 360 degrees, but I want to find the different pieces. So this is a formula. So to go from percent to degree, all right? If I want to go from percent to degree, like this is 25%, I want to take the percent, divide by 100, and multiply by 360. All right, this is super important. All right, so that is how we go from percent to degree. So let's put all of these pieces and then we can find the sums. So 25%. Without thinking about it, you might be able to think 25% is a quarter. So what's a quarter of 360? What's a fourth? It's 90, all right? But we can do 25, let me do this in another color. 25 divided by 100 times 360, you put that into your calculator, you're gonna get 90. So this is 90 degrees. 18 over 100 times 360. It's going to give you 64.8. Remember, this is in degrees. 20%, it's going to be a fifth of 360. So 20 over 100 times 360 gives me 72. 30 divided by 100 times 360 is 108. And lastly, we have 7. 7 divided by 100 times 360 is going to give me 25.2. I'm rounding there. So that's how we get all of these pieces. So what is the measure of these arcs? Well, BC, that's that 25%. So that's 90 degrees. AD, it's only 2 letters, so you go the shortest way, but it actually doesn't matter because it's exactly half. That's going to be 180, or you could do 108 plus 72. AE, that's 108 degrees. ABE. So ABE is pretty big. ABE is actually this whole thing except for this 108 piece. So you could add these all together, or what might be quicker is subtracting 108 from 360 because that's the only piece that is missing. And that gives you sorry, I think I made a mistake with my earlier calculations. Okay, I was confused because there looked like a decimal, but there wasn't. 252. So that's 252. AEB. So that's the whole thing except the 7%. So 360 minus 25.2, that gives me 334.8 degrees. And finally, AC, again, you go the shortest way if there's just 2 letters. That's the 25.2 plus the 90. That gives me 115.2 degrees. So that's how we go from percent to degrees. We have a couple of theorems today. So the first is the congruent circles theorem. What does it mean to be congruent? It means to have the same size and the same shape. So the congruent circles theorem is that two circles are congruent if and only if, let me zoom out a little bit, if and only if they have the same radii. All right, we talked about radii with 10.1. Radii is the plural of radius. So the radius is half the diameter. So if two circles have the same radius, they are the same. So in this one, circle A is going to be congruent to circle B. I'm naming them after their centers. If and only if AC is going to be congruent to BD. Now, we know I'm talking about line segments and not arcs because I'm putting that line over instead of the little arc. So that's why notation is really important for this chapter, so we know what we're talking about. All right. Now, I'm going to jump down here to kind of go along with that. To be congruent, you have to have the same shape and size. To be similar, you just have to have the same shape. So the similar circles theorem just says that all circles are similar. So they could be bigger or smaller, but you just have one shape. It's that perfectly round 360-degree shape. So all circles are going to be similar. So we have the congruent central angles theorem. So here you can see that that angle right there is creating that arc CB, and that angle right there is creating the arc DE, and they are congruent. So the congruent central angles theorem says that in the same circle or two congruent circles, so right here it's the same circle, but I could have two right next to each other. So in the same circle or two congruent circles, two arcs are congruent if and only if their corresponding central angles are congruent. So essentially, if you have the same circle, if they're created by the same angle, the length of that arc is actually going to be the same. They have the same degree and the same length. So in this case, if angle CAB is congruent to angle DAE, which it is because they're vertical angles, then the arc BC is congruent to the arc DE. So these arcs are congruent there. All right, and based off that, we have similar arcs. So if they're congruent, they have that same degree and the same length. Similar arcs are just going to have the same degree. So similar arcs may have different radii, but have the same central angle measure. So for instance, I could have this circle right here with little arc AB. If I had a bigger circle, the arcs are going to be similar if that angle right in there was the same. So if they both have angle X, then those arcs are going to be similar. So AB is going to be similar to CD. Not congruent because the circles are a different size, but the angles are the same. All right, and the next will be part 2. So flip your page over.